Dear students, in organic chemistry, a pericyclic reaction is a type of organic reaction wherein the transition state of the molecule has a cyclic geometry and the reaction progresses in a concerted fashion. Pericyclic reactions are usually rearrangement reactions. The major classes of pericyclic reactions along with the bond changes seen in them are electrocyclic reaction, where one sigma bond is made and another pi bond is broken. Cycloaddition reactions that shows a +2 in the sigma bonds and a -2 in the pi bonds. Sigmatropic reaction shows no change either in the number of sigma or pi bonds. Group transfer reactions show a change of +1 in sigma and -1 in pi. Keeltropic reaction shows a +2 in sigma and a -2 in pi bonds. And ditropic reactions again show no change in sigma or pi bonds. In general, these are considered to be equilibrium processes, although it is possible to push the reaction in one direction by designing a reaction by which the product is at a significantly lower energy level. This is due to a unimolecular interpretation of Le Chatelier's principle. Pericyclic reactions often have related stepwise radical processes associated with them. Some pericyclic reactions, such as 2+2 cycloaddition, are controversial because their mechanism is definitely not known to be concerted or may depend on the reactive system. Pericyclic reactions also often have metal catalyzed analogues, although usually these are also not technically pericyclic since they proceed via metal stabilized intermediates and therefore are not concerted. Due to the principle of microscopic reversibility, there is a parallel set of retropericyclic reactions which perform the reverse reaction. It is well established that the diene can only enter in a cycloaddition reaction with a dienophile in the cissoid form, and the rate of the reaction with the open chain dienes depends on the equilibrium proportions of the cissoid and transoid conformers. Thus, substituents in the diene can significantly affect the rate of the reaction, not only by their electronic character but by their influence on the conformer's proportions. So, the pericyclic reactions are classified as electrocyclic reactions, cycloaddition, sigmatropic rearrangements, and group transfer reactions. And we will also study how Woodward-Hoffmann rules are applied to study the pericyclic reactions. Out of the 4 types of pericyclic reactions, 3 types of reactions can be distinguished by the number of sigma bonds made or broken. The following diagram gives a summary of bonds formed or broken. Let us have a look at this diagram showing the types of pericyclic reactions. We start with cycloaddition reactions. The red arrows show us bond making, that is, a sigma bond being made, and the blue arrows show us bond breaking, whereas the sigma bond would break into and form new pi bonds. That is to say, 2 new sigma bonds are formed or broken, so that the delta sigma is equal to plus or minus 2. Next we look at sigmatropic rearrangement. Here again the red arrows are depicting the formation of new sigma bonds using the pi bonds. One new sigma bond is thus formed and as another breaks, so that delta sigma is equal to 0. Next let us look at the electrocyclic reaction. Here one new sigma bond is formed or broken, either ways, so that delta sigma is equal to plus or minus 1. Another unifying theme for pericyclic reactions is the Woodward-Hoffmann rules that govern feasibility and stereospecificity of pericyclic reactions. According to Woodward-Hoffmann rules, the reactions in which symmetry of molecular orbital is conserved involve a relatively low energy transition state and thus are symmetry allowed. In contrast, in the reactions where symmetry of orbitals is destroyed by bringing one or more orbitals out of phase, the energy of transition states becomes too high because of antibonding interaction, and therefore reaction becomes symmetry forbidden. Another important rule is the fact that thermally allowed reactions are forbidden, photochemically and vice versa. Also, the products formed as a result of thermal interactions have opposite stereochemistry than products of a photochemical reaction. It is important to note that symmetry forbidden reaction might as well proceed if sufficient energy is provided to the reaction. So, we will study this in detail. After studying this module, dear students, you shall be able to 1. Know what are pericyclic reactions. 2. Learn about classification of pericyclic reactions. 3. Be able to identify electrocyclic reaction, cycloaddition and sigmatropic shifts. 4. Evaluate application of Woodward-Hoffmann rules to pericyclic reactions. And 5. Analyze which type of pericyclic mechanism is operative in a given reaction. Based on mechanism, chemical reactions are broadly classified as ionic, free radical and pericyclic reactions. Pericyclic reactions are a unique set of reactions that takes place through a cyclic transition state in a concerted fashion and exhibit high levels of stereospecificity. Additionally, for pericyclic reactions, no intermediates have been isolated and the reactions are free from changes in solvent polarity, free radical generators and even catalysts, although lately Lewis acid catalysts have been reported for some reactions. All these reactions are potentially reversible in nature. Unlike ionic reactions, for pericyclic reactions, there is no definite sense of direction to the movement of electrons as the electrons move in a cyclic manner. There is also a difference between a synchronous reaction and a multi-stage concerted process, as in synchronous reaction, all bond making and bond breaking events take place simultaneously, but in a multi-stage concerted process, some events precede others without producing an intermediate state. Most of the pericyclic reactions are concerted and may or may not be synchronous, though some of the pericyclic reactions occur spontaneously, but in major of them, introduction of energy either in the form of heat or light is required. Moreover, products depend upon the source of energy used. Next, let's take a look at the classification of pericyclic reactions. All pericyclic reactions share common features discussed above. They are classified into following four categories: electrocyclic reactions, cycloaddition, sigmatropic rearrangements, and group transfer reactions. Let us begin with explanation of each type of reaction in further detail. Let's start by looking at electrocyclic reactions. Electrocyclic reactions are characterized by the creation of a ring from an open chain conjugated system with a sigma bond forming across the ends of the conjugated system, or opening of a cyclic system under ring strain to give rise to a diene. Electrocyclic reactions are unimolecular in nature. As you can see, the first reaction shows a ring formation, a four-membered ring formation, while the second reaction shows ring opening to generate a diene. The third reaction again shows a three-membered ring formation. Most of the electrocyclic reactions are ring closing and a few are ring opening in conformationally strained systems such as cyclobutene. Electrocyclic ring closing reactions have been observed for cationic and anionic polyene species such as allyl cations as well. If we look at the stereochemistry of electrocyclic reactions, in the following reaction, one stereoisomer gave rise to one specific product only. As you can see, the trans-cis-trans triene resulted in a cis ring formation. In the second reaction, a trans-cis-cis triene results in trans conformation of the new ring. The stereospecificity of electrocyclic reaction can be explained based on the FMO theory, that is frontier molecular orbital theory, especially considering the HOMO of the triene. The mode of bond rotation decides the stereochemistry of the product formed. Now, there are two known modes of bond rotation, namely conrotation and disrotation, as shown in the diagram. If we consider the termini of the HOMO of the triene system, it can be seen that the end groups must rotate in a disrotatory manner, that is, twist in opposite directions when observed front on, to form the new bond. On the other hand, when photoactivated, an electron moves from the HOMO of the triene to the next orbital, that is LUMO. Now, this orbital contains an electron and it is no longer unoccupied. In this photoexcited system ring, it will close in the opposite direction as compared to the thermal system, and moreover the groups will conrotate, that is, they will twist in the same way to form the sigma bond in the new ring. As electrocyclic reactions are reversible, whether ring opening or closing will take place is determined by thermodynamics. However, the stereochemistry of product formed is not influenced by the thermodynamic stability rules. In another example, thermal ring opening reaction of 3,4-dimethyl cyclobutene, which may exist as cis and trans isomers. It gives hexadiene, which may be cis-cis, cis-trans, trans-trans isomer. In the reaction, cis 3,4-dimethyl cyclobutene on ring opening gave only the cis-trans product, while trans 3,4-dimethyl cyclobutene isomer led to the formation of trans-trans diene only. These reactions take place via conrotatory motion about the C3-C4 bond in a 4-member cyclic transition state. Now let us study cycloaddition reactions. Cycloaddition reactions involve concerted combination of two pi electron systems to form a ring system. Cycloaddition reactions are described as I plus j in square bracket additions, when a system of I conjugated atoms combines with a structure consisting of j conjugated atoms. In cycloaddition reactions, the carbon-carbon bond formation takes place without any use of a nucleophile or electrophile. Among the pericyclic reactions, cycloadditions are most abundant and useful set of reactions. 4+2 cyclization is most common type of cycloaddition reaction. Diels-Alder reaction falls in this category of cycloaddition reactions. The utility of this reaction lies in two simultaneous C-C bond formations which, with suitable substrates, may lead to creation of 4 new stereogenic centers in the product. In Diels-Alder terminology, the two reactants are referred to as the diene and the dienophile, as you can see in the reaction given. Cycloaddition reactions involve bond formation at the ends of both the reacting molecules. This requires proper orientation of orbitals so that effective overlap may give rise to product formation. Reactions where the new bonds being formed are on the same surface are called suprafacial on that component. For the 4+2 cycloaddition reaction, since the new bonds are being formed at the same surface, so the reaction is suprafacial on both the diene and dienophile as well. Following are various arrangements of orbitals in 4+2 pi systems that may give rise to suprafacial and anterofacial orbital overlap to give rise to bond formation. On the other hand, anterofacial reaction requires bond formation between orbitals at two different surfaces. Almost all pericyclic cycloaddition reactions go by suprafacial mode on both the components, as anterofacial overlap would require a most unusually long and flexible conjugated system. This suprafacial approach therefore makes stereochemistry of products predictable. That is, if the diene with substituents at each end forms new bonds to one surface, the product will have a preserved stereochemistry. 1,3-dipolar cycloaddition are another important class of cycloaddition reactions. In this reaction, molecules with 1,3 dipoles, for example azides, ozone, nitro compounds, react with alkenes or alkynes or their heteroatom substituted analogues in a 3+2 cycloaddition fashion, giving rise to cyclic products. As an example of 3+2 cycloaddition, substituted ethine undergoes 1,3 dipolar addition with azides to give triazoles, as shown in the reaction. For photochemical cycloaddition, if the total number of electrons is 4n, then the cycloaddition is feasible. As a result, alkenes give 4-member ring in photocycloaddition reactions by self-coupling or by cross-coupling. Chelotropic reactions are a special group of cycloaddition in which the two bonds are made or broken to the same atom. Thus, sulfur dioxide adds to butadiene to give an adduct for which the sulfur has provided a lone pair to one of the sigma bonds and has received the electrons in the formation of the other. It is an oxidative addition to the sulfur dioxide changing oxidation state of sulfur from +4 to +6. Next, let us talk of sigmatropic rearrangements. Sigmatropic rearrangements are a class of pericyclic reactions defined by the migration of a sigma bond adjacent to one or more pi systems, with the pi systems becoming reorganized in the process. In the reaction, the total number of sigma or pi bonds does not change, as the reactant and the product have the same number of bonds. The sigma bonds that migrates may be in the middle of the system or at the end of the system. These reactions are intramolecular in nature and generally do not require a catalyst for their completion. These type of rearrangement reactions are labeled by using two numbers which are set in brackets, I and J. These numbers refer to the relative distance in atoms at each end of the sigma bond which has moved. Sigmatropic rearrangements 1n are common for hydrogen atom shift, with known examples of n equal to 2, 3, 4, 5, 6, 7 and even for longer chains. As you can see some of the examples, we have the first reaction is a 1,3, the next one is a 1,5, then we have a 1,7. If the hydrogen leaves one surface of the conjugated system and arrives at the other end of the same surface, the reaction is said to be suprafacial. On the other hand, if the hydrogen leaves one surface and arrives on the opposite surface, it is called antrafacial. For these reactions, the feasibility of reactions due to stereochemical constraints is governed by the total number of pi electrons present in the substrate and mode of reaction. If the total number of pi electrons is 4n plus 2, then suprafacial pathway is allowed, and if the total number of pi electrons is 4n, then antrafacial pathway is allowed. You can see the first reaction being suprafacial and the second reaction is 8 electrons and hence antrafacial. The 3,3 sigmatropic rearrangement of 1,5-dienes or allyl vinyl ethers, known respectively as the Cope and Claisen rearrangements, are among the most common and important sigmatropic reactions. You can see Claisen rearrangement showing 3,3 shift and the Cope rearrangement again showing a 3,3 shift. Now let us talk about group transfer reactions. Unlike all the pericyclic reactions that we have discussed so far, group transfer reactions involve a pericyclic process where one or more atoms, group of atoms get transferred from a molecule to another. Therefore, group transfer reactions do not have a specific conversion of pi bonds into sigma bonds or vice versa. Group transfer reactions are less common than other types of pericyclic reactions, and like all other pericyclic reactions, they too are concerted and follow the Woodward-Hoffmann rules. Ene reaction is among the most studied example of group transfer reactions. The reaction between an alkene which has an allylic hydrogen is known as the ene, and a compound containing a multiple bond, that is the enophile, is known as ene reaction, which is also termed as alder-ene reaction. They resemble 1,5 sigmatropic rearrangements since a sigma bond moves, and they also resemble cycloaddition like Diels-Alder reaction, with one of the pi bond of the diene being replaced by a sigma bond. Nevertheless, since the reaction is bimolecular and no ring is formed, they are neither sigmatropic nor cycloaddition reactions. Following are some examples of ene reactions. electron withdrawing groups on the enophile and electron donating groups on the ene favor the reaction. Lewis acid catalysts such as AlCl3 also lead to rate enhancement for the ene reactions. Next, let us look at the Woodward-Hoffmann rules and pericyclic reactions. Out of the 4 types of pericyclic reactions, 3 types of reactions can be distinguished by the number of sigma bonds made or broken. The following diagrams give us a summary of number of bonds formed or broken, depending upon the type of pericyclic reaction. Another unifying theme for pericyclic reaction is the Woodward-Hoffmann rules that govern feasibility and stereospecificity of pericyclic reactions. According to the Woodward-Hoffmann rules, the reactions in which symmetry of the MOs is conserved involve a relatively low energy transition state and thus are symmetry allowed. In contrast, in the reactions where symmetry of orbitals is destroyed by bringing one or more orbitals out of phase, the energy of transition state becomes too high because of antibonding interaction and therefore reaction becomes symmetry forbidden. Another important rule is the fact that thermally allowed reactions are forbidden photochemically and vice versa. Also, the products formed as a result of thermal tractions have opposite stereochemistry than products of a photochemical reaction. The following table shows the Woodward-Hoffmann selection rules applied to various pericyclic reactions, where one can see that if a reaction is con-rotatory under thermal conditions, under photochemical reaction it will be disrotatory and so on. Here A stands for anterofacial and S for suprafacial. It is important to note that symmetry forbidden reaction might as well proceed if sufficient energy is provided to the reaction. Let us now summarize what we have learned in this module. 1. Pericyclic reactions are a group of reactions that take place via a cyclic transition state in a concerted fashion. Pericyclic reactions can be induced either thermally or photochemically. Pericyclic reactions are highly stereospecific. Pericyclic reactions are classified into 4 different classes, namely electrocyclic reactions, cycloaddition reactions, sigmatropic rearrangements and group transfer reactions. Electrocyclic reactions are characterized by creation of rings from open chain conjugated systems or opening of cyclic molecules under ring strain. The stereochemistry of electrocyclic reactions is decided by conrotatory or disrotatory motion of orbitals for effective overlap. Cycloaddition reactions involve concerted combination of 2 pi electron system to form a cyclic product. Stereospecificity in cycloaddition reactions is maintained by supraficial or anterofacial interactions of orbital symmetry. Sigmatropic reactions are defined by movement of a sigma bond adjacent to one or more pi systems with reorganization of pi systems in the process. Group transfer reactions involve transfer of one or more groups or atoms from one molecule to another in a pericyclic reaction fashion. Woodward-Hoffmann rules govern all the pericyclic reactions. A reaction forbidden by Woodward-Hoffmann rules may still take place with an input of large amounts of energy.